Hello everyone. In our journey of seismic design and ductile detailing of reinforced concrete buildings, we have introduced you to a problem statement where we have highlighted some of the beams and columns and beam column joints for seismic design. Today we will discuss about how do we do the seismic design and ductile detailing of reinforced concrete beams, so that you can continue with the example problem. So, whenever you are given any member to design, our first task will be to see whether there is any factored axial compressive stress. If the factored axial compressive stress, which will be calculated by factored axial compression divided by the cross sectional area, if that is less than 0.08 FCK, then the member will be classified as a flexural member and the design will be governed by section 6 of IS 13920 2016. This section 6 details the guidelines related to ductile detailing of beams. However, if the factored axial compressive stress exceeds 0.08 FCK, which will be true for all the columns and inclined members, but sometimes due to some action it might be true even in case of a beam which is a horizontal member, then in that case we need to follow guidelines provided in section 7, which is for columns and inclined members. Okay, once it is confirmed that the current design will be following section 6, then we will discuss the design guidelines for the beam now. So, when it comes to beam geometry, we have some limitations related to the cross section of the beam for good seismic resistance. For instance, the first constraint is about the maximum depth of the beam. The depth of the beam cannot exceed 1/4 of the clear span. What is the rationale behind this? The rationale is that if you have a very deep beam, the beam will tend to have a shear failure, and shear failure is brittle in nature. So, in order to have a ductile failure, we will restrict the depth of the beam. Further, the width of the beam has both minimum and maximum value. The minimum width of the beam is 200 millimeters. You cannot have a beam which is lesser wide than 200 millimeters, because in that case the torsional resistance of the beam will be very poor and the beam will not be able to sustain lateral loads. Further, the maximum beam width is governed by the size of the column beneath the beam. So, the maximum beam width can be 3 times the column dimension, or the column dimension plus 1.5 times the column dimension in the other direction. However, in view of good seismic performance, I would recommend you to not have beams which are wider than the column dimensions. Though the code permits you up to these values, but still you should not have a beam which is wider than the column which is beneath it. Further, the width to depth ratio of the beam is also restricted, which is bound to have a value greater than equal to 0.3, and obviously this value will not be more than 1, because in beams usually the width is smaller than the depth. Why? Because the depth of the beam contributes to its flexural capacity. So, you will always have the depth which will be larger than the beam width, but the beam width cannot be smaller than 30% of the beam depth. Typically, if you have some experience in designing of reinforced concrete buildings, you will say that this will always be followed. Now, once the geometry of beam is decided, we will design the beam for flexural action, which means we need to design the longitudinal reinforcement. How will you design the longitudinal reinforcement? We will look into the design steps towards the end of this session, but before that let us look into the various ductile detailing requirements imposed by IS 13920. The first one is that at least 2 numbers of 12 mm dia bars are to be used at top face as well as bottom face, that is the minimum. Further, the total longitudinal steel, which comprises of top bars, bottom bars, side face bars, should have a minimum value of 0.24 square root of FCK divided by Fy. Now, this is the ratio of these reinforcement bars to the total sectional area, which is BW times of D. So, this rho minimum had this very value which is given over here. On the other hand, the maximum value of longitudinal reinforcement, that is rho max, will have a value of 0.025. This will be more clear when we check in our design example. Then further, near the column face, that is near the supports, the bottom steel should be at least half of the top steel. Why is it said so? Because at the column face we will usually have hogging moment. In case of hogging moment, you will need tension steel at the top and compression steel at the bottom. Usually you need more of your tension steel, because steel is good in tension, and that is why you are using it in the reinforced concrete members, right. So, your top steel there will be of course more than the bottom steel, but this bottom steel should be at least half of the top steel. This is because during earthquakes load reversals can take place and the section can go into sagging moment, and the other section which was earlier in sagging moment can go into hogging moment. So, because of this risk of stress reversal or moment reversals, your bottom steel should be at least half of the top steel, not less than that. Further, at any section, top or bottom steel should be at least 1/4 of the top steel at the column face. So, this is also because of the same reason that at any point of time during earthquake, any of the fibers, whether it is top or bottom, can go into tension or in compression or into repeated cycles of compression and tension. Alright, then further, when a beam frames into a column, particularly an external column, exterior column, where you will have an exterior joint. So, at this joint, these bars, these longitudinal bars from the beam had to be extended to some distance. That distance is called anchorage distance. So, for this bar, the anchorage distance is from the column face up to the end. So, we will assume that both of these bars, that is the top bar as well as bottom bar, all these bars are in tension. Why? Because the development length is highest in case of tension. We will see why do we need development length over here, and any time during earthquake the load reversal can take place and any of these can be in tension. So, that is why we will assume that both of these bar sets, that is whether it is top reinforcement or bottom reinforcement, these are in tension. So, the anchorage length is given by the development length plus 10 times of bar diameter minus some allowance for 90-degree bends. At this point, I would like to tell you that the development length is calculated using this very expression, which you can find in IS 456 at clause number 26.2.1. I have given you the source so that you can go and have a better look over there, because it again depends on tau Vd and bar diameter. So, tau Vd is the design bond stress, which again depends on the grade of concrete. It is given over here in IS 456. Then the development length is typically in practice taken as 50D, which is the highest value possible, but you need to calculate it for a better estimate. Then the allowance for 90-degree bends is typically ranging around 8 to 10 times of bar diameter. We will have a look further when we look into the design example. Once we have designed our flexural reinforcement, we need to understand that we need to have some splices as well, because there will be beams which will be going for several spans and the steel reinforcement is available in length of 12 meters at max. So that is why you need to have a splicing. So let us look into a splicing. A splicing is where you need to discontinue your longitudinal bar, but you want to continue, so you will have to provide some splicing. So you can either provide lap splicing like this, or you can use mechanical couplers over here, or you can have the welded splice. Whenever you are using a lap splice, you need to have a minimum lap length where both of your longitudinal bars are present. Why? Because this bar has to transfer tension or any other force to this bar, and that minimum lap length will be equal to the development length of the largest longitudinal bar in tension. Sometimes the lapping is done between bars of different sizes. For example, you are discontinuing a 20 mm dia bar and you are going to use 16 mm dia bar further, then the lapping has to be there, but in that case the minimum lap length will be the development length of the larger bar in tension. And wherever you are providing this lapping, for example here you have provided this lapping, then the stirrups or the transverse reinforcement, which are usually called as stirrups or ties, they will have closer spacing. As you can see over this zone, the spacing between stirrups is lesser, and this spacing cannot exceed 150 millimeters. In a typical building design, you will find that most of the times in lapping regions you will have a spacing somewhere around 90 mm, 100 mm, 95 mm, 110 mm and so on. Further on, this lap splice should not be provided at certain locations. It should not be provided within a beam column joint. So at a beam column joint, your beam reinforcement, the longitudinal reinforcement in beam has to continue all through the joint. You cannot have a lap splice within a distance of 2D from the column face. Okay, further on, wherever you are expecting that there will be a formation of plastic hinge or flexural yielding will happen in case of seismic loading, then near to that point up to a quarter length of beam you cannot have the lap splice. Okay, so that way you are already limiting the zone of lap splicing. Then at a given location you cannot splice more than 50% of steel bars. Why? This is an over conservative approach that you cannot have this, but typically in the lapping region the force transfer is happening from one bar to another, and that is why you do not want all the bars to be engaged in that force transfer rather than silently doing their task of carrying out the tension. Further, if your longitudinal reinforcement is larger, say 32 mm dia or even larger, in case of girders and all, they are not very common in buildings, then in that case you can use or you should be using mechanical couplers. These mechanical couplers should be conforming to IS 16172 and capable of developing a specified tensile strength of spliced bars. Then these are to be provided within a distance of 2D from column face. You can provide them, that is not a problem, as in the case of lap splices. And the spacing between adjacent longitudinal bar, this is another problem which we have detected while using mechanical couplers, because in mechanical couplers you will have two reinforcement and there will be a coupler which will be connecting both of them, and that couplers will have a larger diameter than the bar. So, to avoid congestion and to have good compaction of concrete in the members, the spacing between the longitudinal bar from this bar to this bar to this bar, you need to know the dia of the mechanical coupler that you are using, so that you can have sufficient space between various longitudinal bar. Now, at this point I would also like to tell you that these days, even in residential buildings which have usually beam longitudinal reinforcement of 16 mm and 20 mm dia, people are using mechanical couplers because it saves a lot of steel and therefore it is making your building very economical. But again, when you are using mechanical couplers, be careful that your spacing between two longitudinal reinforcement is going to reduce because of the diameter of the coupler. Further, we can also have welded splices in which two reinforcements or two bars will be welded to one another, and again the regulations related to where you can provide welded splices is very similar to where you can provide the lap splices. Again, you cannot have more than 50% of steel bars spliced at the same location. Okay, all these guidelines are contained in clause 6.2 of IS 13920. I suggest that you keep one copy of this ductile detailing code handy at your desk, so that you can look into these clauses, so that you are comfortable reading through the pages of the code as well. Once we have designed the splicing of the longitudinal reinforcement, it is time to design the beam for shear. So, when you are designing a beam for shear, what shall be your design shear force? So, one answer is that you need to perform a numerical modeling and analysis where you will get the factored shear force as per the linear structural analysis. So, this you can obtain from any of the commercial software as well. However, in case of good seismic resistance, you also need to consider this part where it is factored gravity shear force, which is only because of gravity loading, that is dead load and live load, considering partial safety factor of 1.2 for dead load as well as live load, and then you need to add equilibrium shear force considering that plastic hinges are formed at the ends of the beam. So, here we will consider two cases. One is for sway to right and another is for sway to left, which means for a given frame, if the sway is happening to the right, the beam is likely to go into double curvature bending in case of moment resisting frame, and when we are having sway to the left, again the beam is likely to go in double curvature bending. So, these two cases are shown over here as well. So, we have tried to calculate. So, these expressions from IS 13920 detail the value of the shear force at end A, at end B. Similarly, for the second case, for end A and for end B. So, as you will find that in this case, we will be considering the design shear force at support A or the near support A to be the maximum of this value and this value, and the design shear force at B shall be the maximum of this very value and this very value. Now, another thing which you will be observing over here is that there is a factor of 1.4 over here. This factor of 1.4 helps us to preclude or have the flexural failure in the beam before the shear failure. Since we do not want shear failure to happen, we shall be exaggerating or we shall be increasing the design shear force itself. So, that is why this factor of 1.4 is present over there. Now, these expressions are also available in code IS 13920. You can have a look over there. Once you have this design shear force with you, you choose the larger value out of these two approaches, that is the factor shear force as per the linear structure analysis and factor shear force based on this assessment. Once you have this, then you look into providing transverse reinforcement. In case of seismic resistance, the minimum diameter of stirrups, as they are usually called, or the minimum diameter of the transverse reinforcement is going to be 8 millimeters. For non-seismic applications, you can still use 6 mm dia stirrups, but when you are designing a building for seismic resistance, then you should not be using 6 mm stirrups. You are forced to use 8 mm stirrups as minimum. Further, looking into the geometry of these links, we will be providing only vertical links. We will not be providing any inclined links. Why? Because in case of earthquakes, when there is a shaking, then in that case the load reversal can take place, and if there is a load reversal, inclined stirrups which were very good at some point of time will be totally ineffective when the load is reversed. Therefore, you should only use vertical stirrups, and even in practice also these days you will hardly find anyone using inclined stirrups. Inclined stirrups are good only when you know the nature of loading to be either tension in one direction and compression in the other, but not load reversal. Okay. Then the normal practice is to use the closed loop, which is made up of a single bent bar, means only one bar is completely bent and that will have 135-degree hook. Okay, but you can also use two bars. In that case, you shall be using a U-link and another will be a cross tie. I have shown it over here. So, if you see, then on the left side, these are for a single bar which is bent in a closed rectangle with 135-degree hook over here. By 135 degree we mean that the bar will be bent by 135 degree. So, whenever, so especially for site engineers, you need to look at the site as well. Whenever there is a tying of reinforcement, at that time make sure that your stirrups are having closed loop with 135-degree hook like this. Then in these figures it is shown as two different bars. One bar which is in the form of U stirrup with 135-degree hook at both the ends, and another bent bar is a cross tie which is having 135-degree at one end and 90-degree at the other end. Again, these bends or the length of these bent bars has to be at least 8 times of the bar diameter, which means if you are using a 8 mm stirrup, then in that case the length of this extension shall be at least 8 times of it, that is 64 millimeters, but never less than 75 millimeters. So, it has to be less at least 75 millimeters. If it is a 10 millimeter stirrup, then you can go ahead with at least 80 mm of this length of the bend. Okay. Further, whenever you are placing these transverse reinforcement in a beam, then this hook should be on alternate side, which means that if you are having this transverse reinforcement, if for this transverse reinforcement the hook is on this side, in the next transverse reinforcement the hook will be on this side. It is very common site practice and it is mostly followed at various sites, but you need to have a look for good quality site practice. Further, as we have seen earlier that at locations of splicing we have closure spacings of stirrup. Apart from that, we also have closed spacing of stirrup close to the beam column joint. Okay, for a given beam, near the support or near the column face, you will have a stirrups which will be closely spaced. What shall be the spacing? The spacing shall be at max d by 4. What is D? D is the effective depth of the beam. What is effective depth of the beam? It is the distance of tensile reinforcement or the bottom reinforcement from the top of the beam. It is shown over here in the figure as well. So, the spacing should be at max D by 4 or 6 times the diameter of the smallest longitudinal bar or 100 mm, whichever is the smallest. Here we are talking about whichever is the smallest, because we want the closed spacing. The spacing is always expressed in terms of maximum possible spacing. The spacing of these stirrups cannot exceed any of these values. Okay. Further on, this zone near the beam column joint, as I mentioned, this will be having a length of 2D, 2 times of the effective depth of the beam, or it can be close to any other possible location of flexural yielding. But as we have mentioned earlier, we expect the flexural yielding or the plastic hinges to form near the beam ends in the beam. So, that is why from the column face up to distance of 2D, you need to have closure spacing of stirrups, which will be having the spacing not more than these values, and the maximum spacing of links over the remaining beam length will be D by 2. So, there you have little relaxation. Further, the first stirrup close to the column face will not be far from the column face by more than 50 millimeters. So, that is also restricted by the code. Now, once we have looked into various design and ductile detailing guidelines as per IS 13920, let us summarize design steps for a reinforced concrete beam. I understand that most of you would be familiar with the design of a reinforced concrete beam from your course on RC design or reinforced concrete design, but I will summarize it over here so that in the upcoming class you can understand the example problem better. So, our first task when we are designing a reinforced concrete beam will be to arrive at a beam cross section. The beam cross section is usually taken as the depth to be taken as 1/10 of the clear span, typically for a simply supported beam or a beam in a moment resting frame and so on. However, it must satisfy the ductile detailing requirements which we discussed for beam geometry in this class. Then we will calculate the design bending moment using dead load and live load, and then we will calculate the limiting bending moment, MU limiting. What is limiting bending moment? Limiting bending moment is the maximum bending moment that can be carried by a beam which is having reinforcement only in the tension, which means a singly reinforced beam can carry at max moment which is equal to MU limiting. So, if your design bending moment MU is less than equal to MU limiting, then you can design the beam as singly reinforced beam, and if your MU exceeds MU limiting, then you will be designing it as doubly reinforced beam. Once you know that, then you can find out the neutral axis and you can estimate the required area of tension steel if it is singly reinforced beam. In case of doubly reinforced beam, AST1 will be given by the area of steel required to carry MU limiting, and the remaining moment, that is MU minus MU limiting, will be taken care by AST2, and both of these are components of the tension steel. So, the total required area of tension steel shall be AST1 plus AST2, and the area of compression steel will also be required, which shall be given by this expression, because we will need compression steel to carry the moment which is remaining from MU limiting, which means MU minus MU limiting. Here we shall look into various terms as we go through the example problem, and after designing the longitudinal reinforcement, we need to check that the provided longitudinal steel must satisfy ductile detailing requirements as listed earlier. We should also be designing a splicing and anchorage suitably. Then we will calculate the design shear force. We have seen in detail how do we obtain the design shear force, and after calculating the design shear force we shall be finding out whether we need to, after finding the design shear force, we will calculate the nominal shear stress, design shear strength of concrete and maximum shear stress. What is nominal shear stress? Nominal shear stress is calculated as VU, that is the factor of design shear force divided by the product of width of beam and effective depth of beam, that is the shear area BD. So this you can calculate. This is like demand. Now let us look into the capacity. So this is the design shear strength of concrete, tau c. It depends on grade of concrete and percentage of longitudinal reinforcement, and can be assessed from table number 19 of IS 456. So this gives you what is the design shear strength of concrete, how much the shear only concrete can carry. Then maximum shear stress, this is tau c max. This depends only on grade of concrete and is obtained from table 20 of IS 456. Now if your tau v, which was demand, is less than tau c, less than or equal to tau c, then you do not need to provide any transverse steel reinforcement, but you need to provide some minimum transverse steel reinforcement as per the codal guidelines. If your tau v is somewhere between tau c and tau c max, then you need to design your transverse reinforcement. We will see how we will design it, and if your tau v, that is demand, exceeds the tau c max value, then we say that this section is inadequate in shear and you need to increase the section, redesign the section. You need to increase the depth or width of the section to obtain a higher shear capacity of the section. Then we will, if we are designing our transverse reinforcement, then we have the expressions shown over here, which you must be familiar from your RC design course. And if your tau v, that is demand, is less than even tau c, then you need to provide minimum transverse steel, which is also given over here. Okay, and this provided transverse steel must satisfy ductile detailing requirements, which we have discussed in this class. In the next class, we will look into the example problem related to ductile detailing of RC beam. Thank you.